In this lecture, I'm going to give an introduction of analysis of design or control systems. So first question is, what is a control system? So typically for a given system, let's say it can be any type of system, it can be a car, a power system, whatever system we're talking about. So the system typically will have input, may not have just a single input. We use the input to represent a general input, and you have an output. For example, when you consider the car as a given system, now you can give an input like the gas pedal. Okay, so when you hit the gas pedal, it actually gives the input because it gives a different amount of gas. The gas will drive the system, which is a car, at different velocity. Your output will be velocity. Okay, so the given a control system basically talks about if I give you a system, okay, we'll talk about how to describe the system later on. So if you give certain input, it will yield some a given output. So this sort of input-output relationship that corresponds to a given system is called a control system. Okay, so roughly speaking, the control system in this course, we'll talk about two aspects of control system. One is the analysis of control system. So analysis of control system talks about if I give a system, what if I give a certain input? So naturally you can see if I give an input, you have output. So the first question will be, if I give an input, okay, so what is the output? What is the output? Okay, for example, if I talk about a car, what if I hit my pedal? So what kind of velocity do I get? Okay, what is the velocity I can get? Okay, or how the velocity will change if I hit the gas pedal according to whatever I want to hit. For example, I hit it really hard or really soft. What is the response or what is the outcome of my system, which is the car? Okay. So basic question for the control analysis is to solve the problem. If I give a control input, what is the output? We should know that. Okay, this is the first question. The second question is the control design problem, which means I want to have certain output. Okay, for example, I want my car to move at 60 miles per hour. This is my goal. So I want this as my output. Okay, so the control design talks about the problem. How do I design a control input? So what kind of input should I give to drive my car at 6 miles per hour? Okay. So this is called the control design problem. So it's kind of opposite. And let's talk about if I already give the input, we want to figure out what is the output. The control design problem talks about if I give certain output, so we want to figure out what is the input. So technically speaking, the control design problem is the harder because we want to use the output derive. We want to give output, we want to derive the input. Typically, it's kind of hard to do, because we have to sort of figure out the control design problem first before we can figure out what's the control design problem. Okay, so now let's first talk about what kind of method we can use to in the system analysis, control analysis. Okay, which means, hey, what if I give you a control input? Okay, what is the output? So before talking about the method used to in the control design problem, we talk about the modeling of a given system, which is also called a description of system. Okay, so the modeling is the main idea of the modeling is to provide a mathematical formulation to describe the relationship between input and output. In other words, okay, before we talk about a control analysis problem, we first have to figure out, we represent the system. We have to talk about what kind of system and how do we represent the system. The best way to solve the control analysis problem is the system better to give some kind of form. It could be an equation, whatever. This one will basically directly tell about what's the relationship between input and output. Okay, so if I know that if I have this model or a mathematical way to describe the relation between input and output, then if I give an input, it's sort of easy to figure out what is the output. Okay, so now let's give an example. What is a system description or description of system? For example, if I talk about a small car or small robot car moving around the horizontal plane, for example, so if we don't talk about the friction between the car and the surface, now I can represent the relation between the velocity and the force we applied, assuming that the force is my input. This is my input, this is my force. Okay, it's also called the input. And let's say this is my velocity, one I control the velocity, or output is my velocity, for example. So I sort of can figure out a relation between the input and output. So F assumes this is the input, and according to Newton's law, I know F is m, which is the mass of the car, for example. A is the acceleration. So F is equal to the mass times acceleration of the car. So because acceleration is just the derivative, double derivative of position, which is also the derivative of velocity. So which means I got a relation between the maximum description of relation between input, which is F, and the output, which is velocity. This is output. So this is sort of a way we can characterize the relation between the input and the output. So input is the force F, and the output with velocity V. Of course, the relationship is described by the differential equation. Okay. So those sort of relationships we want to see, because this is called modeling. I can describe the relation between input and output in a mathematical way. So this is a modeling of a system. Okay. So a lot of times we can represent the system by what we call the ordinary differential equation. So to characterize the relationship between the input and output, which means we sort of can see if I give an input some u, for example, and output is, let's say, y. So sort of the relation is given by sort of ordinary differential equation. It could be something like u is y dot plus 2y plus 1, whatever it means. So this is the kind of differential equation we have. Okay, you might have a derivative of the u, but most of the time it doesn't involve a derivative of u. It involves derivative of my output. Okay, so this type of form is the main form we'll talk about in this class. Okay, so let's say we already have a differential modeling of my system given by the ordinary differential equation. So the next question comes to the fact, how do I solve the ordinary differential equation? Because the ordinary differential equation, as I mentioned before, it describes the relationship between the input and output, which means it already talked about the input relation between input and output. So in other words, the only variable we have is the input and the output in my ODE. So ODE only has its unknown, as my u is input and y. Other parameters we assume they are all known. So in other words, assuming that we already give a u, it looks like we can figure out y, because y is the only variable in the differential equation that can find a solution, right? So meaning that we can solve the ODE with a given input, we can find the output. Okay. For example, if I say in this example, if I say that okay, let's make change a little bit. Let's say this is my v dot. So m times v dot, which is equal to sine t. Let's say this is my f. F is given by sine t, and v is the way I'm going to figure out. To make it simple, let's make m to be 1. So the mass is 1 to make it simple, simplify. Now we can have this. It's v dot is sine t. Okay. Okay, just simplify it because m is 1, so m dot v dot is sine t. So we can just integrate this as v t is integration from, let's assume the starting time is t0 and t is sine t dt. Of course, I have to add on the v0 initial velocity. So my velocity is just given by integration of my sine t from t naught to t plus my initial velocity. So now I can find a solution. Okay, this is the direct method to solve the control design problem, is to just solve the ODE and with a given input. And because the only variable in the ODE that we don't know is just the output variable. Okay, so this method is pretty intuitive and straightforward. One limitation of the approach is A lot of times it's not easy to solve the ODE because the ODE we know it's very difficult to solve because it involves a differential equation, right? It's derivatives. It's hard to solve. Another popular approach that has been developed recently is called many years ago is called Laplace transform approach. The idea of the Laplace transform approach is given by follows. I'll talk about this a little bit lengthy, but I'll try to explain this one in steps. Okay, so first of all, let's see. We have a system modeling, which means we have a model of system. Different. Let's here we say this is the ODE we have, and we have input already. We given input. So in the time domain, if I follow the approach 1, we just have to solve the ODE, okay, and then find a solution. Fine, this is in the time domain. I call it time domain because the derivative, this one means it's a time, okay, right? So this one, because it's a differential equation, there's a derivative, it's hard to solve if this system is complex. For example, if I have x double, no, let's do here. If I have, let's say v double dot t plus v2v dot t plus v plus 2t, for example, which is equal to, let's say input now is t squared, whatever it means. Okay, this one is hard to solve, very hard to solve this one because this one is very not difficult, not easy. Now to solve the problem, another way is why we can do some tricks. So what we do is we can apply Laplace transform to this time domain. I'll talk about Laplace transform definition later on. Okay, assume you already know it, but I'm going to review a little bit about Laplace transform later. So the main idea for this one is I want to apply Laplace transform. The main benefit of applying Laplace transform is I don't have a derivative anymore if I apply Laplace transform. I'll talk about the property of Laplace transform later on. You'll see that. So by doing this, I only have a difference equation in the S domain because Laplace transform actually is you change t to variable to s, so it goes to the S domain. Now, because this differential equation is much easier, so differential typically we are talking about, for example, sx squared s. We don't have this. We don't have squared. We have the cube squared, but we don't have a derivative anymore. So it's easy to solve in this sense. Okay. Now, since it's only a differential equation, and we can solve this one using algebraic equation. This is just, for example, you could have s squared xs plus s times x. You have squared probably this, for example, plus 0 plus 1 over s, for example, let's see, 1 is equal to s squared, whatever it means. Okay, now you can find xs, solve the solution for xs very easily because xs is just equal to change, you move it 1 to the right hand side, you have s squared plus s times xs is equal to s squared plus 1. Now you can find this one solution easily in the S domain. Okay, I don't want to talk about this one in much detail because we'll talk about this more in the later lectures. Okay, so basically speaking, you just find a solution of x. Let's say here you have ODE, your output is, let's say it's a yt over here. Now here it becomes a ys, so you just have to solve ys, and ys is just algebraic equation, so it's kind of easy to solve. Once we find a solution in the S domain, we can use the inverse Laplace transform and try to figure out the solution in the time domain. Okay, I'll talk about this one, inverse Laplace transform, also in the later part. What it does is just try to do a computation, go back to this one. A lot of times this one, you don't even have to compute this. Many times there's a table with that we can look for, and there's a table we'll talk about. If you give specific forms, it will just direct tell you what is the solution in the time domain. So in other words, the approach 1 that I'm trying to talk about here is just don't have this step anymore. It just directly solve the solution in the time domain. Now the second approach, trying to go change it to S domain, solve the solution in the S domain, and then go back again to the inverse to go back to the time domain. It looks like a complicated, but in many cases it can simplify the computation. Okay, now let's go move to the next one. What is the definition of Laplace transform? Okay, and of course I'll talk about inverse Laplace transform later on. Okay, so Laplace transform is defined as this. Okay, so Notation wise, if I give you, so typically it just convert a function in the time domain. This is time domain. I call it time domain. Okay. For example, you can say, hey, I have ft is t. So this is a time domain. So if you apply the Laplace transform, it basically changes it to the S domain, which means you probably have a capital S. So typically we use a little lowercase for the time domain function, and we use f as an uppercase to represent in its Laplace transform. And of course, the variable become S. S could be it's 1 over s squared, whatever it means. So this is like in the Laplace in the S domain by applying the Laplace transform to the original function ft. Okay, so this is just a notation wise. It's the lowercase is represented by represent the time domain, and uppercase is the corresponding uppercase represents its Laplace transform. Okay, in the S domain basically. So the definition of Laplace transform is fairly standard. So Laplace transform given by the integration of e minus st of ft over dt from 0 to infinity. Okay, this is the definition of my Laplace transform. Okay, so let's repeat again. So it's just the integration from 0 to infinity of the original function what I have ft over here, time e to the negative minus st over dt. That's it. That's kind of my Laplace transform. Okay, as for any function you do the computation, you can figure Laplace transform. Okay, so apparently the integration of over t from 0 to infinity, you only have one variable s, so it becomes a function of fs. Okay, so let's talk a little bit like example. How do I compute this? Okay, and so see how complex this would be. Okay, so let's say I have a function f which is given by this. It's sort of, this is called a step function. Let me do this. This is called a step function, which means it is a function when your t is less than 0, it becomes 0, and when your t is greater than or equal to 0, it becomes 1. So you jump, you go move to a step, and it will keep there. It's like you go one step, right? So it's a step function. It's called a step function. So let's talk about a user definition to compute what is its Laplace transform. So according to the definition over here, so it's nothing but integration from 0 to infinity e minus st times ft over dt. Now here, because you integrate from 0 to infinity, right? So ft only defined in the range 0 to infinity. According to the function, so I only have for when it's greater than or equal to 0, so this ft will be equal to 1. So I replace ft by 1 over here. Of course, I can just ignore this. Okay, so when you do this one, so integration of e minus st over dt, right? Here, one thing to remember, this s, you can consider s as positive variable or constant. It doesn't change over time. So you can see this is just as a positive constant. You make a constant, some constant you don't know. You do the integration. When you do the integration of e minus st over t, okay, consider s as a positive constant. So this is just minus 1 over s and e minus st. The reason this is integration, because if I do this derivative of this guy, use the chain rule, it's just one. This is a constant, of course. You only derivative with respect to t, so this is a constant. We just move the constant out. This one use a chain rule. E minus t is e to the minus t again, and then you chain rule the derivative of this guy is minus s. So this will cancel out. You have e minus t. So that's why this integration. Okay, if you have question about this, you can review the integration of the derivative a little bit to understand why this is the integration of that. Okay, and of course I have to evaluate it from 0 to infinity. Okay, so when you go to infinity, when you do the infinity, let's say you do the infinity over here, because s is positive constant, so e minus positive constant time infinity is s time infinity is a positive constant. You do the negative of infinity. Negative infinity, e to the negative infinity gives you 0, right? Of course, 1 minus s also gives you 0. So this is 0 minus, you replace t by 0. It's 1, I must keep this one the same, minus 1 over s times e to the 0. E to 0 is, this is just 1, okay? So this just becomes minus 1 over s, because there's a minus sign over here, so minus and minus will cancel out, so I have 1 over s. So the Laplace transform for this guy turns out pretty simple, just 1 over s. Okay. So let's go to another example. This one is called another function f2t, which is given by this, different. This one is called a ramp function. So when t is less than 0, so this one is defined as 0. So again, when t is less than 0, your ft is 0. When t is greater than 0 or equal to 0, it will increase, okay, as time increases, as t increases, it's linearly increasing. So when t is 0 is 0, when t is 1 is 1, so it's kind of linear form like this. Okay, this is called a ramp function. Okay, so we can sort of follow the same way we computed the Laplace transform for the step function. The difference will be the ft will be different. Okay, so follow the definition. My Laplace transform, I use the uppercase of f2. Okay, is integration of 0 to infinity e minus st time. Here the difference is at t, because when t is greater than 0, this ft 2t is just given by t, so this gets t over here. Alright, so in order to compute how to the Laplace transform, so we do integration by part. Okay, which sort of move this one. What I do is apply a little trick. So we move this one e minus, try to move it to the right hand side after the d derivative. So this one is the same as integration from 0 to infinity t time 1 over minus s time d e st. The reason here, because d e to the est is minus s, you use it in chain rule, it's minus time e minus st time dt. So if you put it back, because this guy will cancel out this term, and this guy will appear again, so it will be the same as the previous one. Okay. So of course, I can pull this because I integration over t only, so it's not an integration over s. So this is the, you can consider this as a particle, s as particle constant, so you can move it out. So it's negative 1 over s integration from 0 to infinity t e d e minus st. Okay, so this one, the integration I do, this one is equal to, I keep this one the same outside the negative 1 over s, that's the same. The integration inside this guy, this one can be written as integration by part is t time e minus st, 0 to infinity, of course, minus integration from 0 to infinity. I can swap the two, need to swap the two, is e minus st dt. Okay, this one we already know how to compute this. This is just what I mentioned over here, right? It's the same thing, right? And this one I can compute this. When I compute this, so this t goes to infinity, right? So this one can be written as this form. It's called t divided by est minus t, because I put a minus, because e minus t is 1 over est, right? That's it. Okay, right? So that's it. So that's why I have t divided by est, because this one, let's see what's happening. Okay, evaluate 0 to infinity. When this goes to infinity, although t goes to infinity, but e to the st grow much faster. E grow like this. So t grow like the t is like just this linear form. This is just my t. Okay. And my est is grow something like this. Est will grow like exponentially fast. So this one becomes much faster than it. So this one will just be when t goes to grow to infinity. This could be a 0. When t is equal to 0, this is also 0. So this is just 0 minus 0. So this is gone. It's just 0. This term I already mentioned in the previous one, okay, before. So this guy is integration from 0 e to the minus t. So you just do over here. This is just equal to this is just equal to 1 over. So this one, okay, let's do it over here. This one is already given in the previous part, right? Because that's integration is the same thing. Okay, so this is just given by 1 over s, basically. Okay, so of course you don't forget the negative sign. So it's a negative 1 over s. This whole thing becomes 0. This is the integration I talked about in previous step. Examples is 1 over s. So it's negative 1 over s time negative over s, because negative cancel out. So I end up having this is 1 over s squared. So this is how I computed the Laplace transform by using example. So that's all I have for this class. So next one I talk about some of the property of the Laplace transform.